what is this chapter about? So first of all, what we are doing is called actually static optimization. What we will do, we are not going to run the program. We are going to see the text of the program, only the program we are going to see, the text, and on that text we are going to apply some algorithms. These are the optimization algorithms. So today we will see one type of optimization that is called dead code elimination. This optimization today we will see, and actually just for reference we are taking this dead code elimination, but we will see this dead code elimination again in the next lecture. We will see it again. So okay, let's see this optimization. So what we do, we actually employ some algorithms. These algorithms, what they will do, they will scan our text. So they will scan our program text, and on this program text they will try to make some optimizations. Like this for the reference I am taking this optimization which is called dead code elimination. Let's call it DCE from now onwards. Okay, so we will call it DCE, dead code elimination. Okay, so we will see it, what is this this optimization, and it will tell us that you can see when we do this optimization, then it will benefit us in the running time, also in the storage. So in both of them, because nowadays programs are getting bigger and bigger. Okay, and so it is also a matter of concern, like the size of the program and all these things, the size of your intermediate code, all these things are, you can say, they do matter to us, and also the execution speed, definitely that matters to us. So let's see. So first of all, what is optimization? So today we are starting this optimization chapter. So far we have only seen what we were calling SSA and so on. Also in this SSA I need to take some examples, so maybe we can take these examples tomorrow. So like these 5 examples, some students did not understand this 5 function. So, and this is a very important actually, because in from SSA so far 2, 3, 4 questions have been asked in SSA so far. But so far they have only asked questions from the expressions. They have given 4 or 5 you can say 3 address code instruction. So they have given 3 address code instructions, 4 or 5, and in that they were asking how to convert this into SSA form. So far they have only basically asked questions from the expressions and the SSA form of expressions. But in a program, mostly the things that we have, the very popular things that we have are expressions, then we have loops, then we have conditional statements. So these are basically the most important part of any program. So we should know how to convert these things, into SSA. We should know how to convert these things in TS. TSE means 3 address code. Also we should know how to convert these things into control flow graph. This we will see today. This uses our 5 functions. So let's cover it tomorrow, because in these slides I don't have this SSA. This is in our previous slides that I have already shared. Either you can go through those slides and you can try to understand, or I can take this in the next lecture. Okay, this TSE we have already covered. So today we will cover this CFG. For all these type of information, for all these type of instructions, we will try to make CFG, because this CFG is going to help us in optimization. We will see it how. So today we basically the target of today's lecture is to see how this CFG, control flow graph, is very important in our optimization process. That is our target. So first let's see the introduction to optimization. What is optimization? Optimization is basically you are transforming your program into another program. You have a program, okay, and you are transforming this program into some other program, maybe shorter program, okay, maybe shorter program, because if you remove some instructions, let's assume some instructions are useless instructions. If you remove them, let's assume there is a while loop. Okay, this is the while loop. Let's assume some condition, some n greater than, as long as n greater than 0, this will be running. This while loop will run. Let's assume that in this while loop all the useless instructions are there. For example, s equal to 1, s equal to 2, s equal to 3, so s equal to 4. Let's assume these 4 instructions are there. You can see actually these are useless instructions. All these 4 instructions can be replaced with only one instruction, that is s equal to 4. this s equal to 1, s equal to 2, s equal to 3, s equal to 4, all these instructions actually can be replaced with only this one instruction. So you can see this will save a lot of time. Will be saved, because you know, when this program is running, at that time, every time these 4 instructions will run. So 4 n times your program will run, this loop will run. But if you remove these useless instructions and you replace these 4 instructions with only one instruction, that is s equal to 4, then only n times your loop will run. So 4, you can say your execution speed has improved by 4 times. That is a huge gap. That is a huge benefit, you can see. In practical scenario, that is a huge benefit. Here you are taking 400 hours. Here you are taking only 100 hours. Here you are taking 4 seconds. Here you are taking only 1 second. That is a huge gap actually. In Google, whenever you see, if a website does not load for 10 seconds, you are going to cancel it. If a website does not load for 10 seconds, you are going to think that your internet is slow. So even this 10 second is a huge time for us. Okay, like there is a website, I made this website, but that was taking almost 10 seconds of time. It was 2 years back. So it was taking 10 seconds of time to load. Anyway, so it was feeling like a decade. This website was feeling like a decade, like it is taking a decade of time. So you can see, this is a huge benefit in our execution speed. So anyway, what is this optimization? Optimization basically means code transformation to improve program. What do we mean by improvement? 2 things we mean. The main thing is that we want to improve the execution time, and the second thing, this is also important, but this is main thing. Of course, execution time matters a lot. Okay, and this is the second thing, that reduce the program size. So this you already know, like this is the meaning of optimization. We have some many algorithms we have so far, and all these algorithms actually do something to improve the program. Okay, so this is our definition of optimization. Okay, now for example, we will see today we won't see this constant folding. Today we won't see, we will see it after 1 or 2 lectures we will see. But basically this optimization can be done at high level or low level. Today we will see this, like we will see how to do optimization at high level. Also we will see how to do optimization at low level. These 2 things we will see today. This constant folding, this thing we will see maybe tomorrow. So anyway, this is our definition of optimization. Now optimization must be safe. What is the meaning of safe? The meaning is this. Let's assume that you have this while loop. Okay, let's assume this while loop you have, and in this while loop you have these useless statements, s equal to 2, s equal to 3, s equal to 4. You have these useless statements. See, you can replace all these 4 statements with s equal to 4, no problem, because this will be safe. Because whenever you will run this program, whenever this program will be run, okay, you can guarantee one thing you can guarantee, that these 4 instructions, when you replace with this instruction, nothing is going to change. Like your outcome is not going to change for any execution. For any whatever execution you do of this program, and say whatever execution you do for this program, you can see both are going to give you the same result. Okay, so that's why your optimization should be safe. Like your optimization should not do like, maybe your optimization is doing like this. You are doing something, okay, and when you are doing this optimization, at that time, maybe for some execution this program is giving some other output, and this program is giving some other output. This should not happen. So okay, don't worry, we will take examples and all these points will be clear. Okay, so optimization must be safe. Must be safe means execution of the transformed code. So this is your source code, and this is your transformed code. So execution of this code must yield the same result as the original code for all possible execution. This is very important point. For every possible execution, okay, this should yield the same result as this. Then this will be called that your optimization is safe. Okay, so and see one more thing. Why I am focusing on this all possible execution? The point is this: Actually, you are doing static analysis. In the last lecture also I told you, in that SSA lecture also I told you, you are basically doing static analysis. Means you have programmed text, either maybe in high level or maybe in low level or maybe in 3 address code or maybe in SSA form. In some form you have this static code, basically this text you have in some form, either in intermediate form or maybe in high level form, any form, but this text you have. On this text you are applying these algorithms. All these algorithms that we will see, these algorithms we are applying on this text. So basically we are not running the program. So when we are saying all possible executions, execution means you are running the program. Okay, so basically when you are doing the static analysis, you need to take care of the dynamic analysis. Dynamic analysis means when you run the program. Now when you run the program, then there might be many executions possible. Okay, there might, like when you run the program, then there might be maybe this becomes true, so you can take this, you can take this, and so on. When you run this program, then many executions are possible when you run the program. Wait a second. So when you run the program, then many executions are possible. All these executions, actually all these possible executions, every possible execution, actually you should take care while you are doing this static analysis. So while you are doing this static analysis, automatically without running the program, you should take care of all the executions possible. So we will see this thing. Okay, but this is the important point. So let's see this. As I told you, we will take for reference this dead code elimination. So this dead code elimination is a optimization technique. This is a very, like you can say, this is one of the most crucial technique, because it will remove direct complete instruction. It will remove. So when you remove a complete instruction, then it is going to benefit you a lot. Like I told you, in this while loop, if you are removing these 4 instructions, these are the 4 instructions you have. 4 instructions you have: s equal to 1, s equal to 2, s equal to 3, s equal to 4. Basically here you are assigning 1 to s, here you are assigning 2 to s, and so on. So when you replace these 4 instructions with 1 instruction, basically you are removing these 3 instructions: s equal to 1, s equal to 2, s equal to 3. You are removing these 3 instructions. This is called dead code elimination. So basically you are eliminating these 3 instructions. This is a huge benefit, because you are removing complete instruction. The complete instruction you are removing. So it is going to benefit you when these instructions are in a loop, because it is going to significantly reduce the, you can say, the number of instructions that will be executed. So anyway, let's see this. So safety of code transformation usually requires certain, wait a second. Nothing is visible. Ankit is saying. Everyone else, you can see, right? To everyone else, everything is visible. This. Okay. Okay, so let's see this. So let's take this example. Let's take this example. What it is saying, dead code elimination. So this is the code it is given to you. The 5 instructions are there. What statement are dead and can be removed? Just look at this program and just like don't worry about compiler design, don't worry about algorithms, don't worry about anything. Just by looking at this program, can you say that some instruction is dead code, like this instruction can be removed without any worry? Without any worry we can remove this. So any instruction, what are the instructions that you can say that can be removed? What are the dead instruction basically? Okay, so someone has said 4th. Any other instruction that you can remove without any worry? Okay, 4th. Yes. Okay. So you see, 1st and 4th instruction actually can be removed without any worry. First of all, why? Let's see this instruction 4th. This instruction 4th can be removed because you see, this instruction is what it is doing. It is assigning z the value 1, and in the next instruction the z is being assigned the value x. So anyway this assignment is not used. Are you getting my point? This assignment. Also, let me tell you one thing. Some students actually make notes while I am teaching. Don't make notes. Just listen. Do not make any notes, because anyway this slide I will provide you. Okay, so all these slides I will provide you. So what I'm saying, see this assignment, first of all, yesterday in the last lecture I told you one thing. Assignment is what? Definition. When we are doing this, when we are studying this compiler design, assignment is nothing but definition. Basically, when you are doing this, when you are studying intermediate code representation, and when you are studying code optimization, these things when you are studying, then assignment is a definition. Basically, here you are defining Z. Okay, don't compare this with your C language. In C language, you are saying that every variable should be defined once. No, that this is different thing. Here, this is also basically here also we are defining Z. Here also we are defining Z. Okay, here we are using Z. Here we are using Z. Here we are using Y. Here we are defining X. Here we are defining Y. Here we are using Y. Here we are defining X. Here we are using X. So this is the basically use and definition. So in yesterday class, I told you something called def use chains. So I don't think that this is in the syllabus. They have not mentioned this in the syllabus, but anyway, this is something called def use chains. Okay, definition to use, we make a chain. Okay, for example, here is the definition and here is the use. So we make like this type of chains we make. So this is also one type of optimization technique. But anyway, the point is that this is a definition. Assignment is definition. Here we are defining Z. Here also we are defining Z. You can see one thing, that this assignment or this definition is not used anywhere. This is the point. This assignment, this definition, this is not used anywhere. You can just see. So that's why this is dead code elimination. So this is dead code because this definition is not used anywhere. So that's why this is dead code. Let's see if any other code is a dead code or not. Let's see whether this is dead code or not. We do not know whether this is dead code or not. Don't say that this is dead code because we are not, because maybe this is just one basic block. We will talk about what is basic block. We will talk about it right now. Okay, let's assume that basically there is some other program, maybe. Okay, some other program is there, maybe. Okay, so anyway, the point is that this is not dead code, but this Z equal to 1 is definitely a dead code, because you can see, as this Z equal to 1 will not be used, even in the further program, this Z equal to 1 will never be used anywhere. Okay, because this definition will not be used anywhere because of this, because now from onwards this Z will be used. So that's why this Z equal to 1 is a dead code. So we can eliminate this instruction. Let's see if any other instruction can be eliminated or not. Can we eliminate this? No, we cannot eliminate this, because this definition is being used here. This definition we are using here. Can we eliminate this? No, this definition we are using here. Can we eliminate this? Let's see whether this definition we are using somewhere or not. This definition, just look at this X. This X, are we using somewhere or not? No, we are not using this X anywhere, because you can see this is the definition and this definition is not used anywhere, because here actually we are using, but here we are using this definition. So are you getting this point, that this definition we are not using anywhere? So this is a dead code, this is a dead code, and we can eliminate. This is called dead code elimination. So actually we have covered it, but we will cover it again tomorrow, because actually today my aim is not to cover dead code elimination, but this is your dead code elimination. If you have a definition which is not used, which is never used, you can guarantee that it will be never used, but you have to guarantee that it will never be used while you are running the program. Basically, see what I'm saying, just understand this. Just by looking at this text, you have to guarantee that if you run this program, then in all the executions, this will be basically, this will not make any effect. This is, so you can see actually we are not running the program, but we are making one thing sure, that if you run the program and you can consider all the executions you can consider which are possible, but still this code can be eliminated. Similarly, still this code can be eliminated, because anyhow you execute them, in all possible ways you can execute this program, you can see that this code is useless. This instruction is useless. So anyway, this is our dead code elimination. and you can see here we can eliminate this, we can eliminate this. So this is the point. You can see need to know whether values assigned to x at 1 is never used later. You can see this is the assignment, this is the definition, and this definition, this assignment is not used anywhere. You can just see. Okay, but we need like how algorithm will do it, we will see at a later point of time. Right now we are not worrying about the algorithm, we will worry about it at a later point of time. Right now our only worry, right now we are just trying to understand how to do this anyway. So we need to determine, like we need to know. So how to know this we will see at a later point of time. Right now just by look, because this is a small program, only 5 instructions are there, then just by looking at this program we can determine which are dead code or not. But when you have a complex program, then you need some sophisticated algorithm. So that algorithm we will study at a later point of time. But anyway, the definition of dead code elimination is this, that if this definition is you are not using anywhere, then this is called dead code. Okay, now of course this is obvious from the simple example. Without any control flow graph, without any algorithm, we can do this. But when you have complex program, when you have complex structure, then you need control flow graph. Okay, you need control flow graph at that point. So let's see more examples. Let's see this example. Now basically this is slightly complicated, more complicated than the last example. Can anyone tell me, first of all, is this x equal to y equal this code, this instruction, is this instruction dead? Tell me only about this instruction, is this dead or not? Just look at this program. Why you are thinking that this is no? Let's see. Yeah, tell me. But in middle this x is redefining, right? This x is being redefined. So very right. Right. Yes, correct. So you can see that this is not a dead code. This is not a dead code because we don't know what is the value of. First of all, we are doing this static analysis. Okay, and in the static analysis, if you see this line, if d equal to, so at this point of time we do not know what is the value of d. Okay, so we cannot take any risk. Like you can that meme, I should have put that meme here. कोई risk नहीं लेने का, that Babu Rao meme. So you can see you can't take any risk here. Okay, like in some execution it might happen. In some execution it might happen that this becomes false. Then what will happen? Then this definition will be used here. So that's why when you are doing this static analysis, just by looking at this program, when you are doing this analysis, at that point of time you cannot remove this instruction. You cannot remove this instruction. But when you are doing dynamic analysis, of course we are not doing it from our gate point of view. We are not doing this dynamic analysis. When you will go to ISC, then I already told you in the last class that there are two courses in the first PAV. There are 2 courses in the first semester. In the first semester you will have these 2 courses. One is PAV, another is dynamic programming analysis. So here actually they do static analysis, here they do dynamic analysis. So when you are doing this static analysis, then you cannot remove this instruction. Maybe when you are doing this dynamic analysis, then maybe you can remove it, I don't know. But right now we cannot remove it. So let's see this z equal to 1. Is this dead code? Is this dead code? This is dead code. This definitely is dead code because you can see whatever execution you do, whatever possibility you do, anything you can do, you will see that this definition will not be used anywhere. Because it is being basically like this z equal to x, you are just doing this. So this definition you are not using anywhere. So that's why this is still a dead code, so you can remove it. Okay, can anyone tell me, is this dead code? Is this dead code or not? Why this is not dead code? Yes, maybe in some execution, maybe I don't know about the I don't know about what will happen in the runtime when we will run this program. I don't know what will happen, but it might happen that this D becomes true, this condition becomes true. Then what will happen? This definition will be used here. So that's why this is also not a dead code. Similarly, this is also not a dead code, because it might happen that this D becomes true and this definition will be used here. So this is how you can check whether if they, of course, in GATE exam they are going to give you very simple program, they will give you in the GATE exam. Such type of program they can give you. Okay, 5-6 lines will be there, nothing much. From the GATE exam point of view, I think this dead code elimination is over. But anyway, I won't take any risks, and I will see it. The algorithm we will see tomorrow. But anyway, this is the point. So let's see here. So you can see you might use this X here. This definition you might use here. Okay. In some execution, maybe on some execution, basically here is the point. On some execution, maybe this D becomes false and you will use this like. So that's why this is not a dead code. So statement is not a dead code. On some execution, value is used later. So this definition is being used here on some execution. So that's why this is not a dead code. Let's see this example. Let's take this like slightly complicated example. Tell me x equal to y plus 1. Is this dead code? Is this dead code? So why this is not a dead code? In the last instruction, you might use it in the last instruction. Actually you can use it here also. So you can say this is not a dead code. No, this is not a use. Actually, this is not a use. Sorry. You can see this is definition, this is definition. This is not a use. As soon as you are done speaking, kindly turn off your microphone. So keep your pointer on the microphone. As soon as you need to speak, you turn it on, and immediately you turn it off. Okay. So anyway, actually this is definition, this is definition. So anyway, but anyway, this is not a dead code, because it might happen that you go inside. Okay, you go inside, you run this. So this definition is run. Maybe this becomes false. Now maybe second time this while condition becomes false, and hence the definition of this X will be used here. So this might happen. So on some execution, basically you might use this definition here. Remember, this is the definition, this is the use. But remember, this is definition, so you don't check like this. I made the mistake. So definition and use you need to check. Definition and use, def use. This is called def use. So this you need to check. Anyway, so this is not a dead code. Can you say z equal to 1 is a dead code or not? Can you say this? So this is also not a dead code, because this z equal to 1, you might use here. You might use here. You might use here also. This z equal to 1. Okay, because this loop will run. So this definition you can use again here. You can use again here. So this is why this is not a dead code. So this is how you basically check whether some instruction is dead code or not. Now you can just see, if I give you this s equal to 1, s equal to 2, s equal to 3, s equal to 4, like this type of instruction if I give you, then you can see in the beginning of the lecture I gave you this type of sequence. You can see this is dead code, because this definition is not being used anywhere. So this is dead code, this is dead code, this is dead code, this is not dead code. So you can see that's why you can eliminate these things. Actually this was our dead code elimination. So this is our dead code elimination. Anyway, so here you can see on some execution, you can see this z equal to 1 might be used here on some execution. Okay, similarly this x equal to y plus 1, this is also not dead, because on some execution you might be using it here. Now let's see few things. You can see we have taken 3 examples because we were increasing our complexity. Like we are taking complex examples, complex programs we are taking. So you can see when you take more complex examples, more complex programs, if you take, then maybe you can't do this like just by looking at the program. Right now we only have few instructions, okay, then we can do these things. But when we will have many complex program, we will have many you can see many branches will be there, many loops will be there, okay, inside return statement will be there, break statement will be there, so many things will be there. At that point of time, you cannot do this type of analysis, this type of optimization you cannot do just by looking at, like we are doing so far. We are not using any algorithm, nothing we are using. So but the compiler design, of course the program, they will use some algorithm, they need some algorithm. So now to develop the algorithm, we need something called control flow graph. Most of the optimization actually use the control flow graph, and using the control flow graph, many optimization will just become very easy. This dead code elimination, liveless analysis, actually this is called liveless analysis. This dead code elimination is also similar to liveless analysis. Basically we can say that here this variable x is alive, okay, here this variable z is alive. Anyway, this we will see tomorrow, but the point is that we need to make a control flow graph so that we can do optimization easily, so that we can write optimization algorithms. This dead code elimination algorithm we can write, constant propagation, copy propagation, many other algorithms we can write. So we need something called control flow graph. So for example, if I give, as I told you, you can do optimization on the high level language also you can do. So for these examples, you can see this is example of high level program. So we are doing optimization on the high level program, okay. Like when you will go to ISC, and in this PAV course, actually all the programs will be high level programs. So you will be doing your optimization on the high level programs. You will be doing some project and these kind of things. I think you will do pointer analysis. So we did pointer analysis. We made a program which was doing pointer analysis. So this is part of optimization. Okay, in our program, what we did, in our project, what we did, we were just looking at statically, just by looking at this program, just by looking at the text of the program, we were determining whether at some point of time, for example, this is our instruction, let's assume this is the instruction I100. So we developed the algorithm which what it was doing, just by looking at just by taking this text. So in that algorithm, you give this text as a input, and this algorithm, what it will do, it will tell you that at this I100 instruction, at this instruction, some pointer p is null, like some pointer p is dangling pointer. So this type of algorithm. So you see, like these all things are optimization algorithms, okay. Anyway, this is just for your motivation, like these type of things you will be doing once you go to ISC. These programs, this algorithm, actually you will write, this complete implementation you will do, okay. So it will be of 20 marks. Anyway, so this pointer analysis we did, you can do something else also. So now you can do your optimization on the low level code also, okay. Like this is low level code, assembly language code. So on this code also you can apply the these optimization algorithms. But here you can see this is more complicated. You can see this is much more complicated, okay. You can see, you can just after this lecture is over, you can just look at this program and you can try to do. So you can see doing this optimization, okay, so far we were having high level program, just 5 instruction, 10 instruction, and just by our naked eyes, without any algorithm, we have done the optimization on the high level program. But just try to do your optimization on this type of program without any algorithm, without any control flow graph. If you try to do, like, you will see how hard it is. So that's why we need something called control flow graph. We need some algorithms. So anyway, right now we won't see this example. We will revisit this example after some slides. After some slides, I have revisited this example. This we will do using the help of control flow graph. We won't do it directly. So we will make control flow graph for this program, and then we will see, okay, how to eliminate the dead code. We will see this, okay, after making CFG. So you can see harder to eliminate dead code in low level code. So we need something, some tools, some mechanisms, some algorithms. Let's see. Optimization and control flow graph. So applications of optimization, see, you can see when you are doing this optimization of when you are doing this dead code elimination, or you are doing something else, no one is going to tell you that okay, this is dead code. So this is not a explicit information. You need to somehow extract this information from the program. Okay, so like no one is going to tell you that this is the dead code, this is the dead code. No, you need to see, you need to analyze the given program, you need to apply some algorithms, and you need to extract that information, okay, so that you can do your optimization. So basically your information will not be explicit. Your information you need to extract. Now you can see, so dead code elimination we need to know if variables are dead at when assigned values. So whether the variable is dead or whether the variable is alive. So we need some algorithm to do this. We need some procedure to find whether a variable is dead or not when it is assigned values. Basically when it is defined at that time whether some variable is dead or alive. Okay, so what is the required information for this? You can see the required information is not explicit. The required information we need to extract. Okay, also we are doing the static analysis, so we must compute it statically at compile time. We cannot run it because we are studying compiler design, and compiler design means we are not running the program. Okay, at compile time we are doing all these optimization. All these optimization that we are doing, all these optimization we are doing at a compile time. So at compile time, of course, we are not running the program. We are not doing dynamic analysis, remember. So, but of course, when you are doing this static analysis must cover the dynamic analysis. Okay, so as we have seen, like your static analysis should cover all the possible executions. Okay, so is this point clear? If anyone has any doubt in this point, then you can ask. So basically your static analysis should cover every possibility that can occur. You can't take any risks. Okay, like on execution, maybe you are taking a risk that you are just doing some possibility, like you are just assuming that okay, maybe this execution will not occur. So at static time, if you take this assumption that maybe this particular execution will not occur, because let's assume that there are 10 to the power 10 to the power 10 to the power, these many executions are possible. Let's assume these many different executions are possible. Then out of these many executions, if you are just taking one possibility that okay, this one execution has only this possibility, this will not occur. So if you take such type of such type of risk, if you take, then that is going to be disastrous. Let me tell you a story. You can check it out on Google. So there was a rocket. So right now I don't know the name of this, but this was a very huge project, and this rocket was sent, and this went to the sky, and it got blasted. So this is a real experiment. I will let you know what is the experiment. When did it happen? I will let you know today. I will send on WhatsApp. So basically here, when they analyzed everything, then they found that actually this mistake, okay, you can see how much money actually they must have spent on this one rocket and on this project, and everything just got, you can say, just got ruined. Okay, so you can see, and the mistake, when they analyzed it and when they did the inquiry, then they found that the mistake was that I think the mistake was like this. They were having only 32 bits register. They were using only 32 bits register, but the information was getting truncated. So actually the information needed 64 bits. Okay, but they were using 32-bit registers. So this type of mistake was there. You can see this type of programming mistake was there, and because of this one programming mistake, because of this small mistake, actually you can see this real incident happened. So anyway, that's why actually you can see this point is, that's why important. So basically you must characterize all the possible executions. You cannot take any risk. Every possible execution you need to cover. You need to think, in your mind you need to think that this execution may occur. If this execution occurs, then what will happen? So basically you need to think that all possible executions can occur, and considering that all possible executions can occur, then you need to do your static analysis. Anyway, so control flow makes it hard. So you should read about this story. You should definitely read about this story. So this is a computer, you can say, programming disaster it was. So much money got wasted, so much time got wasted. You can see many things just because of this programming mistake. This was this small programming mistake. So anyway, so so control, now actually we will make control flow graph, and from this control flow graph we will try to extract the information. Let's see. So what is this control flow graph? In this, you already know this control flow graph. In control flow graph we have something called basic blocks, B1, B2, B3 and so on. Some basic blocks we have. Okay, and so our control flow graph is a graph, just like graph. In this graph, the nodes are basic blocks. We will see what is a basic block, we will see. And the edges are basically saying that this, from this block you can go to this block. Maybe basically from here to here the flow is possible. The flow is possible from this block to this block. So these edges will tell you the flow. The edges will tell you the flow. And this basic block is our node of the control flow graph. So let's see one by one. So what is control flow graph? Control flow graph is a graph that will represent our basically the flow of execution. It will represent statically it will represent all the possible execution orders. Okay, so what are the in this graph? Of course this is a graph, so we must have vertices, we must have edges. What are the vertices? The nodes are basic blocks. And what is a basic block? Basic block is set of instructions. This is like basic block is nothing but a set of instructions. Okay, I1, I2, I3 and so on. Some set of instructions such that in this basic block the flow can enter here and the flow will exit here. Basically from you can see from middle of this basic block you cannot go out. Okay, it's like this. Maybe as like this program, s equal to 1, s equal to 2, s equal to 3. This we wrote in the beginning of the class. So this was one basic block. Because you know one thing, that once you go to this statement, you will definitely go to this statement, then you will definitely go to this statement, and then you will definitely go to this statement. Then you will come out here. So you can see, for example, this is not a basic block. If I write like this, let's assume I write like this, s equal to 1, s equal to 2, if s equal to 3, if s equal to 3, s equal to 4. If I write like, wait a second, yeah, if I write like this, wait a second, yes, if I write like this, then this is not a basic block. Why? You can guarantee that from this statement you will go to this statement, from this statement you will go to this statement, but from this statement either you can go to this statement or you can go to out. So basically from the middle of the block you can go to out, you can go out. Okay, so from the middle of the block you can go out. So this is not a basic block. Basic block means sequence of instructions such that your flow will enter here and your flow will exit here. So you can guarantee that these instructions will execute sequentially without any jumps in the middle. So these basic blocks will help you a lot. Most of the optimization technique that we have in our GATE exam, if you have seen the syllabus, they have added something called local optimization. In our GATE syllabus we only have local optimization. So local optimization means what? You have a basic block. Inside this basic block you will do optimization. Okay, inside this basic block you are going to do optimization. This is called local optimization. Okay, what is global optimization? Global optimization means basically this within, like you can say between these blocks, if you do some optimization, then that is called global optimization. In our GATE syllabus we have local optimization. That's why this basic block concept is a very important concept. So this is the basic block concept. A straight line basically. Okay, single entry code and no branching except at the end of the sequence. So basically you should not have any branch. If your flow is entering here and your flow will exit from here, there is no such thing. Okay, so basically no branching should happen except at the end of the sequence. This end instruction can do some branching. Maybe you can do like this. Maybe this is a like s equal to 2, s equal to 3, and the last instruction is s equal to, if s equal to 2. Now this is a this is a basic block. Yes, why? Because you can see the flow will enter here and the flow will definitely exit here. So this last instruction can be branch instruction. It can be branch instruction. Okay, it is allowed to be branch instruction. Anyway, so you can see the nodes are basic blocks and the edges are what? Edges. So you have a basic block and you have a basic block. Let's assume this is B1. Let's assume B2. Then you have edge from basic block B1 to B2. So it will mean that it is possible that flow will go from here to here. It is possible. Remember, this is just a possibility that flow will go to here, from here to here. For example, maybe you have this type of situation. Maybe you have this type of situation. Here you have B1, here you have B2, here you have B3. What it means? It means that at runtime, it is possible that your flow can go from B1 to B2, or is it possible that your flow can go to B1 from B1 to B3? So basically, your edge will represent the possible flow of control from the end of one block to beginning of another block, because the basic block definition requires that in your basic block there is only, this is the single entry and this is the single exit. So this is your so this is the definition of edge. Basically this is what edge represents. Okay, so there may be multiple incoming outgoing edges from each block. Let's see this diagram. This is a CFG. You can see for this program, if you make the CFG, then this will be the CFG. You can see these three codes are guaranteed that they will execute sequentially. It is guaranteed that from this code you will go to this code, from this code you will go to this code. This is guaranteed. Okay, so you can see this is your basic block B1. But when you are in when you are at this situation, then either this condition can become true or this condition can become false. If this condition can become true, then this is your basic block, because you know that these two things will definitely execute in a sequential order. Similarly, these two things will execute in a sequential order. So this is your B3. So you can see from this statement, if the condition is true, then you can go to here. If the condition is false, then you can go to here. And whether you have this or whether you have this, the next node will be this. So from here also you will go here, from here also you will go here. This is your control flow graph for this program. Okay, so this is how you can make control flow graph for the high level language code. Remember, this is the high level language code. Okay, and this is the control flow graph. As I told you, you can do optimization on the high level language program also, or you can do the optimization on the low level program also. Most of the time this optimization we will do on the low level intermediate code, like 3 address code or something. So most of the time that we will do, but the concept actually, like in GATE exam, they can give you high level program also, because the conceptually this is also allowed. Like you can do optimization on the high level language code also. Anyway, so let's see basic block. So what is a basic block? You already know, sequence of consecutive statements such that there is basically the entry at the beginning of the sequence and you will leave from the end of the sequence. Okay, it's like this. So incoming control, you can have multiple incoming edges, you can have multiple outgoing edges. So this is your basic block. In the basic block, the instructions will definitely execute in a sequential manner. There is no such thing from the middle. There is no such thing. No branching in and out in the middle of the basic block. Neither you can come in nor you can go out in the middle. So now you can see these are the basic blocks, B1, B2, B3. These are the basic blocks. Okay, and edges are basically telling you that there is a possible flow, control flow. For example, there is, when you are executing this program, then it is possible that from B1 you can go to B2. From so basically this execution order is possible. This is one possible execution order. This is another possible execution order. So this is how you can make. You can see. So basically this, remember, this CFG models all program executions. This is what I wanted to tell you. So far we have not run this program. We have just seen the text of the program, and just by looking at the text of the program we have made this control flow graph. You can see just by looking at the text. But just by looking at the text we have made this control flow graph, and this control flow graph, this CFG is covering all the possible executions. You can see it is covering all the possible executions. You can see because what are the possible executions like you can have this execution or you can have this execution. All the possible executions are covered by this CFG. So that is the benefit of CFG. CFG will model all the possible program executions. Without running the program, we can cover all the possible program executions. Possible executions. What is a possible execution? That is nothing but a path in this graph. So in this graph, if you have a path, then that is basically your possible execution. For example, you have a path from B to you can see this is a path. You can see this is a path. So this is a possible execution. You can see this is a possible execution. See, there is no path like from B2 to B3. There is no path. You can see in this CFG, from B2 to B3 there is no path. So it tells you that there is no possible execution which will go from here to here. There is no possible execution. Even in runtime, okay, there is no possible execution of this form. So this CFG is modeling all the possible executions, and possible execution is nothing but a path in this program. In this program, if you have a path, then that is your possible execution. Okay, multiple paths, multiple possible program execution, because you can see this and this. So multiple paths are there, so you can have multiple executions. Now so this is one possible execution. You can see this is one execution one means this is one possible execution. C becomes true, then this will be the path. Program executes basic block B1, B2, B4. This is one possible execution. This is another possible execution. If the condition becomes false, then this is another possible execution. Now this control flow graph, actually this control flow graph, as I told you, this is not taking any risk. Okay, like when you are doing this static analysis, when you are making this control flow graph, then actually it should cover the superset of the possible executions. Okay, see maybe when you are doing this, when you are running the program, then it might happen that when you are running the program, at that time maybe some execution order is never possible. Okay, when you are running the program, at that time maybe some execution order is never possible, but still your CFG might have that path. Okay, because as I told you, this CFG cannot take any risk, because without running the program you are doing the static analysis. Without running the program, you are making assumptions about the running of the program. Okay, without running the program, you are making some assumptions like what will happen if you run the program. As I told you in that rocket example, when this rocket was going on, at that time they should have considered everything. They just put like, of course these programmers were not idiot, okay, but still they put only 32-bit. So they only put 32-bit register. Okay, this 32, I think they declared int. They should have declared long int. Actually they should have declared their variable to be long int, but they declared int. You can read about it. This is a real incident. So they should have declared long int, but they declared int. So you can see, because of declaring this int, this much disaster happened. So why this disaster happened? Because these programmers did not consider the possibilities that could have occurred. So you can see, when you are doing this static analysis, at that point of time you cannot take any risk, and sometimes you will consider basically all the possibilities you need to consider. Here these people did not consider the possibility that what will happen if the data basically exceeds these 32 bits. Okay, so they should have considered these kind of things. Okay, anyway, so after this incident, actually to tell you, actually this static analysis it actually started more frequently. You can see the researchers started studying this static analysis more after this incident, because once they got to know that this type of course this programmer was only a person, so humans can make mistake. So that's why these researchers started to finding some algorithms, because algorithms are not going to do any mistakes. So that's why they started to develop some algorithms which will catch this type of mistake, which will catch when programmer will make this type of mistake, then they will catch. So that's why this static analysis, this dynamic analysis is so much important. You can see. Anyway, so you can see, for example, this is one example. You see here what is happening. You can see this is the code. So here you have if C, and in the middle, let's assume this is the program, let's assume, and let's assume here you have x equal to x plus 1. Let's assume this is the program you have. Now you can see if this is your program, then these are the basic blocks you can see. So from the program you have made the basic block. You can see that if this C is true, if this thing is true, let's assume if this C is true, then definitely this C will be false. So you can see if this C is true means from B1, if you are going to, let's call it B2, from B1 if you are going to B2, basically if this C is true, then from B1 you are going to B2, from B2 you are going to B4. Now let's assume there you have B5 here. So now this execution order actually will never be possible. This execution order will never be possible when you run the program. When you actually run the program, then this execution order will never be possible, because if this C is true, then this C will be false. Okay, so when you actually run the program, then this execution order is never going to occur. This is never going to occur. Similarly, if this C is false, then from B1 you will go to B3, from B3 you will go to B4. If this C is false, then automatically, because this C is false, so this will be false. So you can see, wait a second, I made some mistake. Okay, actually I should write B6. Let's assume this is B6. Basically, if this C is true here, then definitely this C is also true. So this execution order can never occur. B1 to B2, B2 to B4, B4 to B6. This execution order can never occur when you run the program. Similarly, B1 to B3, B3 to B4, and B4 to B5. This execution order also can never occur. So these two execution orders can never occur when you actually run this program. When you actually run this program, then these execution orders will never occur. But you can see your control flow graph is not saying that they will not occur. Your control flow graph is saying that they are still possible. You can see, because your control flow graph is saying that this is one possible, because your control flow graph says that possible execution means path in a graph. So in this graph you can see there is a path. So this control flow graph is saying that it is possible that this execution order can occur. But you know that when you run this program in practical life, then this execution order will never occur. So you can see that when you are making this CFG, then this CFG might give you some program, some path, or you can say some possible executions which will actually never occur. So is this point clear? Let's see. So you can see from this is the basically some in the CFG you can have some infeasible execution also. Okay, you can see this CFG will definitely model all the program execution, but it can model some extra which will never occur, but it can model those also. Okay, of course, whatever will actually occur. So these are the things that will actually occur. They will definitely be covered here, but some extra things you can cover here. This CFG can cover some extra things. So this is the point. Now, so this is your basic block. Multiple edges can go out. Okay, like if your last instruction is if instruction, if s equal to 2, then multiple things can happen. Either this will be true or this will be false. So you can see multiple outgoing edges you can have. Okay, so this, when you have multiple outgoing edges, then what it tells you? It tells you that this is also one possible execution order, this is also one possible execution order, and this is also one possible execution order. So you can say that basic block executed next may be one of the successor basic block. Either this, either this, either this. Okay, maybe one of the successor blocks. Each outgoing edge basically tells you outgoing flow of control in some execution of the program. Maybe in some execution of the program this can occur. In some execution of the program this flow can occur, and in some execution of the program this flow can occur. So each outgoing edge actually telling you some flow of control in some execution of the program. Similarly, incoming edges, each incoming edge is basically telling you some in some execution of the program incoming flow of control. Okay, and control may come from any predecessor. Maybe control can come from here, control can come from here, and control can come from here. Okay, for example, if you have let's assume this is your basic block, and the first statement, let's assume this first statement has level L1. So, and let's assume in your program somewhere you have go to L1, and somewhere else you have go to L1. So you can see multiple execution, multiple you can say incoming edges you can have. So multiple incoming edges you can have, and each edge basically tells you that control may come from here or control may come from here. Similarly, you can say that each incoming edge is telling you that in some execution you might have this flow, or in some execution you might have this flow of control. Now, how can we make basic? How can we build a this CFG? So this CFG you can build for high level also or for low level also. Like in the last lecture, I told you this intermediate representation. So you can also have high level intermediate representation. You can also have low level intermediate representation. For example, most of the time actually in the high level intermediate representation we use syntax tree. Syntax tree because you know this thing. This is your lexical analyzer. This is your syntax analyzer. So this syntax analyzer will make syntax tree. This syntax tree is also a intermediate representation. This is also a intermediate representation. Okay, remember, but this is high level intermediate representation. Then you go to ICG, intermediate code generation. This will generate low level intermediate representation. Here you can use SSA or you can use 3 address code. These things I have already told you in the last class. So you can see you can build this CFG for high level intermediate representation also, or you can build this CFG for low level IR also. Anyway, so we will see for both of them, we will see, and let's see. So in the GATE exam they can give you any, I think I think they will give you this high level program, maybe. I think when you are doing this optimization, then I told you in ISC in PAV course we have all the high level code. So we were doing optimization on all the high level programs. So that's why I think that they might give you high level program. But anyway, so in the high level program, how to make a CFG, for high level program, very easily you can make. We will take you can just go through these slides, but I will just directly go to the examples. So let's take this example. First of all, let's take if you have a statement, let's assume there is a statement s equal to 1, simple statement, not a conditional statement, not a while statement, not a looping statement. If you have a simple statement, then this is your CFG. So this is your node. Actually every statement is a node. Right now I am making inefficient CFG actually. Okay, don't worry, because you might be thinking that I should make basic blocks. In the basic block I can put many instructions such that here you start, here you end. So actually right now we are just starting this CFG, and right now what we will do, we will make inefficient CFG, and after this inefficient CFG we will see how to make efficient CFG. So right now these CFG that I am making right now, okay, you don't make this CFG in the exam. Okay, so anyway we can directly go to the next part also. Like for example, you have if you make like this, let's assume this statement you have S1, S2, Sn. So let's assume these are the statements. These are normal statement. These are not branching statement. These are not looping statement. These are normal statement. Then actually either you can do this type of CFG or you can make this type of CFG. Basically you can just make one node. So you can see this is efficient CFG, this is inefficient CFG. Okay, in the further slide we will see that this is inefficient CFG, this is efficient. So actually in your exam you should make like this. Now how to make CFG for this conditional statement? If you have this if then else statement, if you have this type of statement, then how can you make CFG? Very easily. Basically there will be a true branch, there will be a false branch. Simply you can make. Okay, in the true branch this is happening, in the false branch this is happening, and then you are making an empty basic block. Again this is inefficient CFG. In the efficient CFG we will see that there won't be any empty basic block. This empty basic block won't be there. But right now just basically we are building our concept. We are going from inefficient to efficient, and finally we will use only the efficient one. So if you have if then statement, then how can you make? Very simple. You have if then statement, then basically either this condition is true, then you will execute this, or you will execute this. So this is if then statement. There is no else part here. So this is your CFG for if then statement. If you are true, then you will execute this. If you are false, then you will execute this. But you will do like this. So anyway, this is just like you have if conditional statement. Just like you analyze the conditional statement, you can make CFG for it. How to make CFG for while statement? Very easy. This while statement basically says that if this condition is true, means basically if this condition is true, if this condition is true, then you will execute S and then you will come back to it. If this condition is false, then you will just go to something else. So you can see, if the condition is false, then you will go to something else. If the condition is false, you will go to something else. If the condition is true, then you will come back to it. So this is how you will make CFG for while statement. Remember, when you are making CFG for while statement, then again you are not using while. Actually, you are using this condition, whether this condition is true or not. If this condition is true, then you will execute this. If this condition is false, then you will go here. So this is how you will make CFG for the while statement. Now let's make CFG for this program. Very easily you can make CFG for this program. So for example, you know, this is your while statement and this is your Z statement. So first what you can do, you just separately make for while and then you make for Z equal to X. This is okay. Let's unfold it. So it's like this. So basically go one recursively. You can construct the CFG recursively. Okay, recursively we are constructing the CFG. So you can make CFG for this, then CFG for this. So you can see this. Now let's unfold this. How to unfold this? Because this is a while, so this internal thing you can write it as S or body, then you will get this CFG. Now let's unfold this body. Now when we unfold this body, then we will get this. This is a very inefficient CFG actually. Why this is inefficient? The reason is this, because all these two statements, you can see these two statements are sequential statement, so you can put them in one node. So anyway, this is how you can make the CFG. But let's see the efficient CFG now, and this is the CFG that you will use. So actually the algorithm that we have seen so far, this is a simple algorithm. Now you might be wondering, if this was not an efficient CFG, then why did I construct it? See, it was not an efficient CFG, but you can see the algorithm was very simple. This is the point. The algorithm was very simple and you can generate CFG. If you want to generate good CFG, efficient CFG, then of course the algorithm will be more complex. So now we will generate efficient CFG. In efficient CFG, our each node will be a basic block. Each node will be a basic block. Basically, as many as statements we can take, we will take them. For example, okay, so in our CFG, now our basic block will be, so number of basic blocks should be as minimum as possible. Number of basic block should be as minimum as possible. And inside this basic block, we should have as many instructions as we can take. So this is the idea. This is the idea for efficient CFG construction. Okay, so far whatever we have seen, that was inefficient, so you can just forget that. Just remember this efficient CFG construction. This efficient CFG construction says that number of basic blocks should be as few as possible and each basic block should be as large as possible. Okay, and of course what he's saying, there should be no pair. Like what he's saying is like this. It should not happen that this B1 is there. Let's assume this B2 is there. This type of situation should never happen, because in this situation what you can do, you can mix this B1 and B2. This is what he want to say. There should be no pair of basic block such that B2 is successor of B1. You can say this B2 is successor of B1. B1 has one outgoing edge, B2 has one incoming edge. This should never happen. You can see, because if this happens, then what you can do, you can merge this B1 and B2. You can merge them. So this is the point. So this is how you can construct efficient CFG. From now onwards, you only need to focus on the efficient CFG. But actually, I think this was a GRE exam question. In this GRE, I don't remember that question right now, but this was a nice question. They had given some basic blocks they had given. Okay, some basic blocks were given, and they were asking which of these basic blocks can be removed, or which of the basic blocks can be merged. They were asking like this. So they have given basic blocks B1, B2, B3, B4. This was a GRE exam question. So they were asking which of these basic blocks can be merged, and the options were like B1, B2, B2, and so on. So actually this type of situation was happening. There was this type of situation that from here you were going here, and from here you were going here. So actually there was, you can see this is your, let's call it B1, let's call it B2. You can see this B2 was, let's call this B1, let's call this B2. So it was happening that this B2 is successor of B1, okay, and this B1 has one outgoing edge, and this B2 has one incoming edge. So this type of situation was happening. So what you can do, you can merge them. Okay, so anyway, so this was a question I just wanted to let you know. In the GATE exam they can ask you this type of question, because this GRE is I think this was 10 years ago this question came in this GRE exam. Nowadays in GRE computer science exam does not happen, but it was a very nice exam. There should be no empty basic blocks, and also there should be no empty basic blocks. So this is your efficient CFG construction. Okay, now for this program you can construct efficient CFG like this. You can just check it out after the class is over. I will share the notes, and you can check it out that this is your efficient, this is your CFG for this graph. You can see this is your basic block, you can check. Okay, so anyway, this is your CFG. This is how you can construct efficient CFG for the high level code. Now for the low level code, how can you do it? For the low level code, we have this leader algorithm. Some of you already know this leader algorithm, that we can find leaders and we can make basic blocks. Every basic block starts at a leader. So that leader algorithm you might already know. So that algorithm we can use. Okay, so, and in that algorithm, remember this one thing, actually some students make mistake. So let's assume this, you can see this jump L1. Jump L1 means from here actually you will jump to this. So don't put a edge from this to this. Some students put edge from this to this. Don't put, because this is unconditional jump. This is unconditional jump. Unconditional jump means from here you can never go here. From here you will definitely go here. So this is the point basically. You can never make a execution flow from here to here. Your execution flow will be here to here. So that's why when you have unconditional jump, then only one successor will be there. When you conditional jump, then there will be two successor. For example, this is a conditional, where is conditional jump? Yeah, this is a conditional jump, you can see. This is a conditional jump. So you have two successor. If this condition becomes false, then you have this. If this condition becomes true, then you have this. So two successor when you have conditional jump, and one successor when you have unconditional jump. So this, you can see this you can convert into CFG using the algorithm of leader algorithm we will see. Okay, right now we will see this leader algorithm, and using this algorithm you can convert this low level IR into CFG very easily. You can convert. So let's see this algorithm. What is this algorithm? This algorithm this is just a theory of control flow graph. We have already seen this theory. You can just go through this theory after I share the slide. You can go through it, but anyway we have seen this. So basically this is your CFG, you can see. And let me tell you, in the GATE exam you can see there are some questions. Sometimes actually some authors consider this two special nodes. Some authors consider these two special nodes, entry node, exit node. So when you are making a CFG, then some authors put two special node, entry node, exit node. But some authors do not put these nodes. So it depends on author to author. Okay, so like in this question, if they ask you how many nodes are there, then 1 2 3 4 5 6 7 8. Either you can say 8 node, or you can say 6 node, whichever is the option. Let's assume in the option they have given this, then you can answer this. In the option, let's assume this is not given, in the option this is given, then you can answer this. Okay, so because some authors put these special nodes, some authors do not put. So this is an ambiguous thing actually. Anyway, so this is your basic block, straight line. Basic block is nothing but a straight line of code. So this is basic block, this is basic block, and these are the loops and all these things. Let's see the leader algorithm. So this is the leader algorithm basically. First, what you do, first you find the leaders. What are the leaders? First statement is always leader. So this is the first tuple is always leader. Okay, the first tuple, the very first tuple is always the leader. And you can say this, if you have this type of statement, conditional statement or unconditional statement, then the target of conditional or unconditional statement is also leader. So this L will be leader. Remember, target of conditional or unconditional statement is a leader. Now, tuple L is leader if it immediately follows a tuple. So basically, if you have conditional or unconditional statement, then the statement that will follow it, that will be a leader. So this is the very simple leader algorithm. And basic block is what? From one leader to the next leader. Okay, that is a basic block. So let's take example. Let's see this. Let's see this example. So you can see in this example, for this code, you can make, first of all, you can make 3 address code like this. Okay, you can try it on your own. This 3 address code we have already seen in the last class. But anyway, in the GATE exam, they are not going to ask you how to make 3 address code. If they ask you, then they will give you options, and from the options you can eliminate the options. Let's directly take this, and from this let's try to find what are the leaders. So first statement is always leader. So this first statement is a leader. The target of conditional or unconditional goto is a leader. So this 7 is a leader because this is target of conditional statement. The target of, so this 3 is a leader. Okay, anything else? Now the statement that follows a conditional or unconditional jump, that is leader. So this is a leader. Similarly, this is a leader. So you have, these are the leaders. You can see 1, 3, 5, 7, 10. These are the leaders. So what is a basic block? Basic block is nothing but from this leader to before the next leader. So this is a basic block. From this leader before this leader. So basically leader to leader, this is a basic block. Leader to leader, this is a basic block. Leader to leader, this is a basic block, and this is a basic block. So we have 5 basic block. 5 leader means 5 basic block. Okay, and you can put edges. How can you put edges? This is conditional jump. So conditional jump will have 2 edges. One will go to 7, so one will go to here, and another will go to next. As I told you, conditional jump instruction has 2 successor. And the unconditional, there is no unconditional jump here, but if there was let's assume this is unconditional jump, let's assume, then this edge won't be there, because unconditional jump will always have only 1 successor. So this is how you can make. So how many? So 5 blocks will be there. You can see 5 basic blocks will be there, and this is how you can, every conditional jump will have 2 successor. This is successor, this is successor. Every conditional jump will have 2 possible successor. And so this is your final you can say summary. This is just a summary. A control flow graph is nothing, is a graph in which nodes are basic blocks, and we have edge from basic block B1 to B2 if there is a possible control flow from B1 to B2. Okay, so we have 2 special nodes, enter and exit. As I told you, these special, to some authors take these special nodes, some authors do not take these special nodes. Anyway, so we construct a CFG for each procedure. So if you have a procedure, let's assume you have many procedures, then for each procedure you construct a CFG. This representation is used during code generation and optimization. So this CFG we use in code generation and optimization. This we will see tomorrow. So okay, all the slides are over. So you can just go through these slides and all the things that I have left. For example, how to from this code, how to construct this code. Okay, so you don't need to do this. Actually, don't do this, because in GATE exam anyway, this is not a subjective exam. If this was a subjective exam, then maybe you can do this type of thing, but right now you don't need to do this thing. They will give you this type of program. You just need to find out how many basic blocks are there, how many leaders are there, how many edges are there. So far in GATE exam, I think three or four times they have asked such question. On control flow graph they have asked 3 or 4 times. So they can ask this year, they can definitely ask, because for the optimization you need these concepts. Control flow graph, this CFG concept you need for the optimization. Basic block, CFG, all these concepts you need. The flow of control, the edges, okay, all these concepts you need for optimization. So it becomes an important chapter from the GATE exam point of view for this year. And there is absolutely no need to do this transformation from this code. How you got this 3 address code, there is absolutely no need. If you want to waste your time, you can waste, but anyway, there is no need. If you want to do it, you can do it. But the main thing is finding the basic blocks, and main thing is finding the leaders, and main thing is finding the control flow. Okay, putting the edges. Remember this thing, that when you have unconditional jump, then you only have one successor. When you have conditional jump, then you have 2 successor. So this is an important point that you should remember. Anyway, so for example, this is your source code and this is your 3 address code. If you want to do the transformation, you are welcome. But actually in the exam you will get this direct code, and in this code you need to do the analysis. Basically from this code you need to make the CFG. For example, remember this is your unconditional jump. So when you make CFG, then you will basically go from this to 2. So you will go from this to 2. So you will not go from this to this. So there won't be any edge from this to this. Anyway, so this is our chapter. We have seen CFG and we have seen the dead code elimination. So the dead code elimination is over, but we will see it again tomorrow. Our target for today was to build CFG, and on CFG we will do optimization. So this real optimization will start from tomorrow onwards. Now from tomorrow onwards, every day we will take one technique. Around 3 or 4 techniques are there. In 4 days it will be over. Okay, so anyone has any doubt today, then you can ask. Sir, can we say CFG or DAG? I guess it's true. No, CFG are not DAG. CFG is a different thing, DAG is a different thing. So this DAG we can study, maybe some other day we can study this DAG, but these are different things. CFG is a control flow graph, and DAG is our, we use DAG in some, we can do common sub expression elimination. This technique, this optimization we can do using DAG. So this DAG is also useful when we do code optimization. At that time this is also useful. Okay, thank you others. Anyone has any doubt? And you should definitely study about that algorithm, that problem, that disaster that I told you. I will share the link for that. I will share the Wikipedia link. You can study about that disaster. That was a programming disaster actually. Anyway, anyone has any doubt? Please send model PPT. Okay, I will send it today. And a little bit announcement. Today I have uploaded 5 questions on our, as I told you, I am putting 5 questions daily. So for the last 2-3 days I did not put any question. So tonight I will put 20 questions.